Hello and welcome to another LeetCode problem. So today we're going to be doing problem number 329, longest increasing path in a matrix. And I don't think this problem is too difficult, so let's get into it. So for an m by n integers matrix, we can return the length of the longest increasing path in the matrix. We can either go up, left, right, or down. We cannot move diagonally, and we cannot move outside the boundary. And so let's look at our first example. So for our first example, our longest increasing path is 4, right? So it's 1, 2, 6, 9. Then the second one, it's 3, 4, 5, 6. Yeah. And in a third one, the longest increasing path, this is the second one. In our third one, we just have one element, so it's 1. So there's a couple things here that are good to point out. Let's actually just draw this first example, and then we can go from there. So let's draw this. Okay. And so we have 9, 9, 4, 6, 6, 8, 2, 1, 1. So for one thing, we need to ask ourselves for these kind of like depth first searches. The thing that matters a lot is, does it matter where we got here from, right? Like, so in this case, so this is asking for, I think this is a strictly increasing path. You can move longest increasing path, right? So you can't move like from 2 to 2. So if it's an increasing path, like let's say we're at the 6, would the count of numbers we can get to from the 6 depend on where we got to the 6 from, or not really? Well, let's see. So where can you go from 6? So 6 can go to 8, or it can go to 9. So either way, it would be a path of 2. Well, let's say we get here from a 1. And now, how many elements can we go to from 6? Well, we can still go to 1. And let's say we get here from, well, actually, this is probably like not the best. Let's actually use some other numbers here. Yeah. Okay, because the 6, they're just like, you can't really go anywhere. Okay, here we go. Let's use this one. There we go. Okay, so let's say we are, what's the longest path here? Let's say it's, yeah, sure. Let's say it's this 4. Yeah. Okay. So from 4, what's the longest path? So we can go from here to here to here. And I'm just going to leave this path. So if you can look, if you got here from 2, you're like never going back, right? So the key thing to recognize about these questions is, because you're going strictly increasing, you don't really need to have like a visited set to make sure you're not revisiting things, because the only way to get to 4 is from lower numbers, right? Like we can only get here from here or from here. And so because we can only get here from lower numbers, it doesn't really matter where you got here from for like the result of how many numbers you can visit from 4. And so this makes this problem a lot easier, because we're not going to be doing repeated work. So like if we know this path, no matter where we start, like let's say we start at this, let's see. I mean, we can't get to 4 through to too many numbers, but let's say we could actually get here like this, even though we can't. It doesn't really matter how we get to this 4. We can only go in one, we can only go, like, we can't revisit, we can't go back down to things that we got here from. So all the paths that we got here from, we can never go back. And so intuitively, this makes a lot of sense on how we would code this up. So what you would actually do is, for every single number that you visited, we can just store like how many numbers you can get from there, right? So it would be like, from this 1, we can get to how many numbers? We can go to the 2, and that's it. So this would be like 2. From this 2, you can't go anywhere, so that'd be 1. From this 2, you can go to a 3, and that's it, so 1. From this 3, you can't go anywhere, so 1. From this 2, you can go to 2, 4, 5, 6, right? So that'd be 4. From this 3, you can go 3, 4, 5, 6, 4. And then from 4, you can go to 4, 5, 6. So that's 3, 2, 1, right? And so the nice thing about this is, no matter where we got, like, we can just store these numbers, and then that'll save us a ton of work. So we never have to redo anything, and so this should be an m by n solution, and it should be pretty straightforward. And the only thing we really need to do is check what would be our result from every single starting number, because that does matter, right? Where we start does matter to get like a maximum. So we can just loop through this entire matrix and then do a DFS, and then if we go to a number that we already have a result for, then it's pretty straightforward, right? So like, let's say we start at this 2, and we haven't been, and let's say we calculated this path already. All we would do is we would just say from 2 to any node that you can go from 2, it's going to be 1 plus whatever their result is, right? So like 4 or 3 or 6, you just get the maximum. So you try to go everywhere you can, and then you just do 1 plus because you are counting the node you're at to the node you go to. And so it's actually, this is a lot easier because it's strictly increasing. If it was something like you could go, to the same node, like 2, 2, 2, 2, 2, then it would be a lot trickier because now you'd have to do like a visited. But here you don't, because you can't really make loops when you're going strictly increasing. So that's the most important thing to know. So let's try to code this up, and I think it should be pretty straightforward. Okay. So what we want to do is we want to have a visited set, remember? And we can just set okay, as default dict. Okay, now what we want to do is we want to make our DFS function. So we're going to have a row and a column. We also do want to have like a rows and columns. So let's do that. Equals length matrix. Okay. Now what we want to do is we want to say, so we can do a couple things. Yeah, actually let's do that. Yeah, okay. So what we can do is we want to have our base case. So our base case is if we can't go anywhere or if we're already in visited. Well, when we can't go anywhere, we'll find that out later. We also do want to have a directions array as usual. So okay. So if this is in visited, we can just return straight away, right? So if okay, so that's done. Now we need to try to go in every single direction and then make sure, so when we do try to go in a direction, like let's say we're here, we need to make sure that the number of views is inbounds and it's greater, then we can try to go there. And so we do want to have a res here as well, because we're going to try to go in every single direction and we're going to try to maximize our output. So we're going to say res equals 1 because it's going to be guaranteed to be 1 because we're already in our cell. Okay, so now for direction in directions, same as always. So n row and column equals row plus direction 0 and column plus direction 1. Now we only want a DFS if we're inbounds and we're going to an increasing location, so we're going to check for that. So if, otherwise we can just skip this. So if n row is going to be greater than or equal to 0, greater than or equal to 0, and is less than rows, and same thing for the column, is less than columns, and so now we're guaranteed to be inbounds, but now we need to check, is our next location greater than the current one? So that's going to be matrix row column strictly increasing, so greater. We are kind of running out of space here. That's okay. Okay, so now we have all our conditions. So we checked for inbounds and we checked for strictly increasing. Then we need to actually go there. And that's going to be, so actually we can make this 0 to start. Okay, so that's going to be res equals max res 1 plus. Remember, we should start at 1, so DFS. So we're going to go to this n row and column. Okay, so now we try to go every direction. We just maximize this result. And then we can just return the res. But first we need to put it in our visited. So okay, and return res here. Okay, now remember we need to loop through every single row and column, and we need to have every single starting value. But what we don't need to do is, like I said, we don't need to reset this visited, because when we get somewhere, it doesn't matter how we got there. So that's going to be important. Okay, so for row and rows, for columns. Okay, now this is going to be, so let's think about this. So we do want to have some kind of other output that we're trying to maximize, right? So this would be another res, I guess. And then we just do res equals max res, and then DFS, add all of these different indices, so row, column. And then we can return here. Okay, let's see. This is range. Make this a mistake every 5 seconds. Range. Okay. Let's take a look here, actually, what would happen here. So we got a 3, you expected 4. Definitely interesting. Definitely interesting. But let's take a look why that is. So let's look at our DFS. So for every, oh, I think I see. Yeah. So this actually needs to be 1. I did forget one case. Yeah, so like let's say we have an index where we can't go anywhere from, like this one. We can't go anywhere, so we will never do this. So we do need to make it 1. We need to initialize it to 1 because if we can't go anywhere, we want to return 1. Okay. All right. And so let's think of the time and space complexity. Definitely an easier hard problem for sure. So time is going to be, remember we're not visiting anything more than once, so m by n. And space, we do have this visited set that we're going to store everything in, so n by m as well. Okay, and I think that that's it for this problem. So if you like this problem, please like and subscribe to the channel. It helps grow it a lot. Thanks for watching, and I'll see you in the next video. Bye.